We're going to do another example, this time using a slightly different idea in terms of the types of problem that we're going to do. We're going to prove that for all positive integers n, 3 to the n divides 4 to the n minus 1. So all powers of 4 minus 1 are divisible by 3. Now let's talk about divides first of all. So divides. So to say that A divides B means that B is a multiple of A. That is, B is equal to A times Q for some integer Q. Okay, some integer Q, and we're only talking about integers here when we deal with this. And I've used the Q here suggestively for quotient because this is equivalent to A divides B gives us a quotient of Q and 0 remainder, and those two ideas are the same, but this one here, the multiple idea is a lot easier to work with. So that's what we're talking about here. So let's dive in. We dive into the proof. So for the proof, we'll let Pn be the statement that 3 divides 4 to the n minus 1. And for the basis step, when n is equal to 1, the statement P of 1 is that 3 divides 4 to the 1 minus 1, because that's what n is in our statement. N is 1. And 4 to the first power minus 1 is just 3, so it is obvious that 3 divides 4 to the 1 minus 1. Thus P of 1 is true. That's our basis step. Like so often, it's pretty straightforward. So now we're going to the inductive step, and let's let k be an integer and assume that P of k is true, again very much like usual, and then let's write down what this means. That means that is 3 divides 4 to the k minus 1. So there is an integer q such that 4 to the q minus 1 is equal 3 times q. Now bear in mind what we want to prove. I'm going to put the scratch work above here so to give us more space below. So up here I'm going to put some scratch work. Scratch. We want 3 divides 4 to the k plus 1, that quantity minus 1, because that would be right here. That's all of what we mean by P of k plus 1. So that is external to the actual written proof, but I did want to put that there so we can look at what we really want. We want 3 to divide 4 to the k plus 1 minus 1. So here's the thing. If we look at what we have right here, then there is probably a way that we can get a hold of the 4 to the k plus 1 by looking at this right here. And in fact, let's do that. So this would say then 4 to the k is equal to 3 times q plus 1, adding the 1 to both sides. Yeah? So that we have right there. And so now we can get a 4 to the k. Thus, 4 to the k, we can get a 4 to the k plus 1, I should say, is equal to 4 times 4 to the k. But 4 to the k is right up here, and that's 4 times n, 3 times q plus 1, which is equal to 12q plus 4. So bear in mind what we want up here. We want a minus 1 there, 4k plus 1 minus 1. So let's subtract 1 from both sides. Then 4k plus 1 minus 1 is equal to 12q. Well, if I'm subtracting 1 here, do you see I'm going to get a 3? Right? So scratch again here. I'm not actually putting this in the proof, but what I've done is I've subtracted a 1 here and I've subtracted a 1 here, which means I get 12q plus 3, and on this side I get 4 to the k plus 1 minus 1. Right, well that's pretty close, because this is equal to 3 times 4q plus 1, and what I wanted to do is show this is divisible by 3, that is, show it's a multiple of 3. But it is then, right? So I'll say since 4q plus 1 is an integer, 3 divides 4 to the k plus 1 minus 1. So this is p of k plus 1. That's statement. So that is p of k implies, when p of k is true, it implies that p of k plus 1 is true. Right? And so that concludes the inductive step. And now we can conclude overall by saying, therefore, by mathematical induction, three divides 4 to the n minus 1 for which integers? Well, in this case we proved it for all positive integers n. And you may find that you encounter a problem or two with this divides concept. There are nice examples of mathematical induction.